This is by Dr. Amritanshu Prasad. In fact, I didn't know his full name. I knew only as Amri. Professor in the mathematics unit. Well, he is now the director of the unit officially. Full-fledged director. He can even say no to this kind of meeting. But he will not. His primary research interests are in combinatorics, representation theory, harmonic analysis, automorphic forms. Professor Prasad has been the faculty member at IMSc since 2003, following a postdoctoral fellowship at University of Montréal. He is an active educator, having taught a wide range of courses from algebra, complex analysis, representation theory, including online courses in NPTEL and IIT Madras. At IIT Madras, his published work reflects a strong focus on the intersection of combinatorics and representation theory. A notable contribution is his book, Representation Theory, a Combinatorial Viewpoint. And it's published by Cambridge University Press. His recent research, often in collaboration, continues to explore areas such as representation theory of symmetry groups, permutation groups, and combinatorial enumeration over finite fields with several publications. So he will talk to us. What is the title you have?
How mathematicians think about symmetry.
How mathematicians think about symmetry, which is slightly different from for others think about symmetry.
Indeed, yes.
Maybe the same. Okay, now the second session of today, up to you, Amri.
So if you just look at me standing on the stage, is there some symmetry here? Yes, so what is the symmetry? So if you were to draw a line down the center, then the left hand side and the right hand side look the same. So that's a symmetry. That's the simplest example of symmetry which we see a lot in our everyday. Yes, so this there's a story about a donkey, and there are two stacks of hay kept on both sides, and they're exactly identical, and the donkey stands in the center, and he's very hungry, and he has to decide which one to eat. But they're both exactly the same, right? So then the story says that the donkey starves to death because there's no way to decide. So that's the essence of symmetry, that you cannot tell between two things. So I'm not perfectly symmetrical, but close enough that that if you draw a line down the center, everything that happens to the left happens on the right as well. So in this talk, I'm going to tell you about different kinds of symmetry. We intuitively see them. For example, we have here a flower. Maybe I'll have a bigger flower too. Yeah, so we have here two flowers, right? So, so this one's hibiscus and this one is, okay, I'm not sure either. So is there something that is same about their symmetry? So it's different from my symmetry, right? Because this flower, for example, is very pronounced that it is not symmetric about the vertical line. If I were to draw a line here, what's happening, even if I were to position it somehow so that this petal is right at the bottom in the center, you'll see that there's a sort of a twirling that's happening. And so there's a very different kind of symmetry in this flower. Now this is also a different looking flower, but it has it has 5 petals, and there's still this twirling happening. And if you ignore the minor sort of imperfections of nature, which actually make it even more beautiful, you will admit that these two do have the same symmetry. So, in what sense do they have the same symmetry, and how do we as mathematicians organize them? I'll show you some more things which are symmetric. So, so one of my hobbies is origami, and this is an origami top. So you can actually put it on the ground and spin it. Anyway, you won't be able to see, but it spins. So it's got a kind of pointy thing here, and you can spin it. And this, well, this also has a sort of symmetry. This actually has, if I hold it like this, you see it has a symmetry about this line, similar to my symmetry, but it has much more symmetry. It also has a symmetry about this horizontal line. Can you see any other symmetries? I can rotate it. Oh, vertical is also there, yes. And maybe I can also do a diagonal, you know, this axis is also an axis of symmetry, and I can also turn it by maybe just how many degrees? Maybe just 1/8 of a full turn, and it looks the same, right? So this also has a kind of symmetry, but I can't flip it around. It's different on this side and on this side. So you could think of symmetry as something two-dimensional, but you could also ask for three-dimensional symmetries. So from my little box of toys, here's another origami piece. So this is a cube. It's an example of what's called modular origami. So it's a fun group activity. So there are several identical modules that we made, and then we put them together to form this cube. Now this cube, okay, so this is a very stylish kind of cube. It has this square, but then there's also a tilted square. So it loses the symmetry about the vertical axis. But it does have rotational symmetry like this. But it has symmetries in other directions. So the three-dimensionality of this gives it more symmetry, right? I could do this, and I could also, there's a very non-obvious symmetry here. If I were to, I don't know if I can point this vertex exactly at you, but maybe I'll draw a picture on the board where this becomes more apparent. So, so if you were to look at a cube, with one vertex pointing exactly at you, there are three edges coming out of it. And if you were to just stare at it like that, it would look something like this. It would look like a hexagon. A hexagon, but with three sort of, half diagonals drawn on it. And you see it has another symmetry, which is rotation by 1/3 of a full circle. So this is a interesting symmetry that you may not have seen at first. Things can get more interesting. So does anybody know what this shape is called? No, a rhombus is a plane figure. So this is called an octahedron. Yeah. So it's one of 5 Platonic solids. So there's I also have another one called so there's the cube. This is called the tetrahedron. So this also has a kind of many symmetries. You could perhaps, it has this 120-degree, rotational symmetry, but it has these symmetries about different axes. So there are different kinds of symmetry. This one has also has a rotation by 90-degree symmetry. If you look at it like this, there are 4 faces that are facing you. You can rotate it by 90 degrees, but it also has a 120-degree symmetry. You sort of rotate it like this. And More interestingly, we have this. This is a kind of stylish dodecahedron. So it has pentagonal faces. Each face is a pentagon, and all its faces are just regular pentagons. And it has, I guess, 12 faces and 20 corners. So this has a different symmetry. It has a 1/5 of a full turn symmetry. Right? So you see that these different objects, they look quite different. Sometimes two of these things have the same symmetry. Sometimes they have different symmetries. This is something that we sense intuitively. Those two flowers I showed you may look somewhat different, but they do have the same symmetry. So, and this symmetry actually plays an important role in a lot of, it has a lot of practical applications. Physicists use symmetry a lot, and symmetry somehow determines how physical laws are formulated. At one level, you could say that Einstein's special relativity, if you've studied Einstein's special relativity, it's axiomatically just a statement about symmetry. So Einstein says that the laws of physics are the same in all inertial reference frames. And if you just think about space-time, these different inertial reference frames are different ways of looking at it. So there are symmetries which take one reference frame to another. And simply by exploiting the symmetry, you can derive all the amazing consequences of special relativity. So it's just pure mathematics. So this is, so there's symmetries of that kind. There's symmetries in chemistry. So you have molecules which have a lot of symmetry. And this symmetry it manifests itself in the wavelengths of light that they absorb. Then you have symmetry in mathematics, which is the symmetry of equations. So that's a bit harder to explain, but this is one of the famous, so one of the origin stories of what I'm going to talk about, the mathematical theory of symmetries. By studying the symmetries of equations, the mathematician Galois was able to show that you cannot solve a general equation of degree 5 by radical. So there's no easy way to solve these equations. So let's start by analyzing, well, let's start with the simplest thing, my symmetry. So what can you do? You can just do a reflection, right? So you can take my left side and make it my right side. I can't actually do this because we live in a physical world. I can never turn my right hand into my left hand. They will always remain. If I turn around, my left goes to my right, but it's not the same thing. It's the back of my hand which looks different from the front of my hand. So there's only one symmetry here, and that you could call a reflection, but it's not really physical. It's a mirror image. So reflection is sometimes denoted by R. So I take myself and reflect. This, one way of thinking about it is it's something you do to transform an object. And if I take that reflected image, so you could do this, for example, on your phone you have this, when you take a selfie, there are two options. One is to mirror it, and where if you move your right hand, the image moves its left hand. And there's the other way to sort of show the actual thing, where if you move your right hand, the image also moves its right hand. So that's the transformation I'm talking about. And if you were to repeat this transformation again, so I take myself, I look at my image in the mirror or in the mobile phone, and then it looks at its image in the mirror. What happens? It comes back to the original, right? So if you take a mirror reflection 2 times, you get back what you started with. If you take my right hand, take its reflection, you'll get my left hand. And if you take my left hand and take its reflection, you'll get back my right hand. So this reflection has the property that if I do this reflection 2 times, so we sort of use this notation in algebra, we write things next to each other to say that I did this and then I did this. Sort of could be left to right or right to left, it doesn't matter. But anyway, I do this 2 times and what do I get? The original, right? The identity, so it's called the identity. I. So now whenever I say that I take some object and don't do anything to it, I'll be calling it I. This is the simplest example of a group of symmetries. So what I study is called representation theory. It's different ways of studying groups of symmetries. So I have this symmetry which is R and RR is I. So that comes back to it. And there are lots of things which have this same symmetry. I think if you look at this TV screen from there, it has a similar symmetry, right? It has it's designed in a way to be symmetrical. Maybe there's some writing on it which makes it asymmetrical, but you know, it has this symmetry, and there's really nothing else you can do to this. Well, maybe you can rotate it by 180 degrees. So that has more symmetries. Can you think of other things besides people and animals which have this kind of symmetry? Alphabets, that's a great, yeah. So some letters of the alphabet. So A. There's only one thing you can do to preserve its structure. You can reflect it about this line. What about B? Yeah, so if you were to write it sort of in a special way, you could reflect it like this. Though we often write the upper thing to be smaller, so then it loses the symmetry. C, D, but I itself, look at this I. This has more symmetry. This has, you can also reflect it about the x-axis, right? So this has more symmetry. F is a letter which has no symmetry at all. You're all natural group theorists, I can see that. Can you think of a letter other than I which has a lot of symmetry? O. X. D. T. T has, T is the same as A, I think. So for the representation theorists, T and A are the same. M. There's something I actually like very much. So what is this? Is it something new? You cannot reflect it. There is no reflectional symmetry. But does it have some symmetry? What is it? Rotation. See, if you reflect it about this diagonal, then it's still not a symmetry because this thing will come here. But if you rotate it by 180 degrees, if I were to take this Z and just rotate it by 180 degrees, then this thing will come here, this thing will go there, and it remains perfectly symmetric. So this Z is a new type of letter. It's not the same as A, it's not the same as X. Are there any other letters like Z? S. So this also has this, you rotate by 180 degrees, it remains the same. So you can classify the letters of the alphabet according to their symmetry. And you can do this very, very intuitively. Okay, so these necklaces you can buy from the gypsies in Besanagar. This thing has 38 beads which are pretty identical. So, so what is the symmetry of this necklace? I can rotate it, right? I can rotate it by 1/38 of a full turn. So if I call that R, then I can do R 38 times, and then I'll get I. I rotate it. This is what we do when we chant a rosary, right? We kind of just keep doing this, and it comes back to the original thing. And the number of times you chant depends on the number of beads. So I will write this sort of as a shorthand, because if I were to write R 38 times, it would be difficult for you to read and it would be difficult for me to write. So we write it as R to the power 38 is equal to I. Does this necklace have any more symmetry? I mean, ignore this thing. Yeah. Right? I can do that. I can take this necklace and I can turn it around. And this is not any of those 38 symmetries. It's different, right? If you look at the positions of the beads, these beads on this side come to this side, and these beads on this side go to that side. So this is completely different from any rotation. So there's this reflection, and so this time I'll call it S. So this is reflection, and this is a rotation. Are there any more symmetries? Oh, that's another thing. Yeah, sure. So in this actually I can also rotate each individual bead. Yeah, so we can do that, and that's a lot of symmetries because each bead can be flipped around by things. So cut it.
There will be two parts.
Okay.
Side will have half.
It's a straight line. There's a straight line.
Yeah, like this. And I would have two more and half.
What? No, but we don't want to change the chain. We want to keep it the same. So symmetry means you don't change things. It looks the same, right? So here I flipped it like this, but I could also flip it like maybe like this. There are lots of ways I could flip it. For the moment, I want to sort of ignore the fact that I can rotate each bead. That is also a valid symmetry. That will lead to each bead being rotated or not. That will lead to 2 to the power of 36 symmetries. But let's assume that these beads were perfectly spherical. So I couldn't find such a chain at home. So a pearl necklace with perfect pearls would do the job. So if I were to do that, I have many other reflections, right? So I have S1, S2, I have lots of reflections. I just have to decide whether I could take a bead and I could reflect around that bead. Or I could take the space between two beads and I could reflect around that. And if you analyze this a lot, you will find that there are 38 of these reflections. Each pair of opposite beads gives me 2 reflections, one by reflecting at the beads and one by reflecting between 2 beads. So you have 38 rotations and 38 reflections, and this would have a symmetry group of 38 plus 38, which is 76 symmetries. And then the ones you pointed out, so 76 into 2 to the power 38, if you allow each bead to rotate. So this has a huge number of symmetries. Okay, so this is, but now this all seems to be getting very, very complicated. Maybe this is too big. Let's take something a little more manageable. So what I do is I'll bring back my cube. The cube is something that we are all quite familiar with. So here's another origami model of a cube, and this one doesn't have those little squares inside it. Cubes are something we're all familiar with. We play dice, we have cubes. We make poriel, we have cubes. So it's a common thing. Octahedron somehow is quite simple but not so common in life. So let's try to understand the symmetries of this. Okay, so the language we're going to use is going to be these kind of symbols which depict individual transformations that we can make, and we'll also think of these as actually physical transformations. So I'll take this thing and rotate it by 90 degrees, I'll give that a name. I'll take this thing, rotate it by 120 degrees, give that a name. And then we can do these things, one after the other. I can first rotate it like this, then I can rotate it like this, and the possibilities seem very large, and how do we kind of put them into a manageable thing? So let's look at this. So here I have already drawn a cube, but I can't see the back half of this. Maybe I'll draw that with a different color or something. So, oh well, there's no color chalk here. Okay. So, so behind this there's another vertex which is not visible to you, and there are these edges. So totally this cube has how many vertices? 1, 2, 3, 4, 5, 6, 7, 8. So what we'll do is we'll keep track of just what happens to the corners of the cube. If I know what happens to the corners of the cube, every point inside the cube is determined by its position relative to the corners. So I'll know what happens to every point inside the cube. And let's look at some transformation. This is a kind of bookkeeping device. So suppose I take this cube. Oh, thank you. So, so we have the visible edges, and then we have the hidden edges. So these are sort of behind, so maybe I should have drawn them. Yeah, okay, there we go. So, okay, so where's my cube gone? Okay, how is it possible to lose something? Okay, here it is. Okay, so what shall we do first? Shall we rotate around the face 90 degrees? So suppose this face 1, 2, 3, 4 is the face that we are rotating against. What's going to happen is that 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 1. Right? That's what happens to these 4 vertices. And then at the same time we can look at 5, 6, 7, 8. What happens? 5 goes to 6, 6 goes to 7, 7 goes to 8, and 8 goes to 5. Okay, we'll call this R. So this thing I'm going to call R. It's a rotation, maybe I'll call it R. Yeah, let's just call it R. So it's a rotation by 90 degrees, and what it does is with this numbering, of course if you can number the vertices differently, it will look different, but let's just fix a numbering of the vertices just to keep track of things. So 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes back to 1, 5 goes to 6, 6 goes to 7. So you see there are 2 kind of cycles in this, the front face and the back face. They kind of move within each other. But there's another kind of symmetry which I pointed out, which is this 120 degree rotation. You fix the vertex, one of the vertices facing you, and then you rotate the things that are adjacent to it. So can you tell me, suppose I fix the vertex 1 and rotate by 120 degrees. What will happen? Yeah, okay, so you could tell me either what happens to 2? 2 will go to 4. So let me write it somewhere. I need to erase. It's in my hand. Yeah. So let's see. 2 will go to 4. So I'll write it like this. 4 will go to 5, right? 4 will go to 5. And 5 will go back to 2. And what else is there? 6. What will happen to 6? No, TRG is not allowed to answer. Yes. 6 will go to 3. Very good, very good. 3 goes to 8. 8 goes to 6. What happens to 1? 1 is still 1. So I'll do it, I'll write it here. 1 goes to 1 and 7 goes to 7. Let's call this, no, we already called this R, so let's call this S. We can call it whatever we like. We can call it, but not R, because we already called this R. Right? If we call everybody the same name, then it will be very confusing. So we'll call this S. Okay, so we've got R, Mr. R and Mr. S. And now the thing gets very confusing. I take this cube, I do R, and then I do S. Now how do I even do S? So I think it has to fix this. I think this is S. So what happened, right? It's very confusing. What happened? But with our little bit of bookkeeping, which using the numbers, we can actually figure out what happens when we do R and then do S. So let's say what happens when we do R and then S. So now it matters, which you do first. So I'm going to write R and S. That means first I'll do R, then I'll do S. Some people they'll say first I'll do S, then I'll do R. So you need to fix convention. Let's say we first do R, then we do S. Okay, so what will happen to 1 if we first do R and then we do S? So when you take 1, where will it go with R? 1 will go to 2, and then S, you do S. So that 2, where does 2 go? 4. So 1 goes to 4. This is when you do R, this is when you do S. So when you do S after doing R, 1 goes to 4. Right? What happens to 2? Three, and then 3. No, we mustn't do 3 goes to S, so S. So 3 goes to 8. What happens to 3? So first we are putting R, so 3 goes to 4, and then we are putting S. So 4 goes to 5. So let's work it all out. 4 under R goes to, where is 4? There, okay, 1. And under S, 1 goes to 1. Oh, that's something interesting. So 4 goes to 1. 5, what happens to 5? 5 goes to 6, and 6 goes to 3. Okay, so you're all now experts in representation theory. This is all we do. R goes to 6 goes to 7, and 7 goes to 7 goes to 7, okay. 7 goes to 8. 8 goes to 6. And 8 goes to 5. 2. Wonderful. So you've just done your first calculation in group theory. So, this is your second one. The first one you did was R into R is I. Well, then you did R into 38 is I. This is your third one. But this is the most interesting one. So if you look at this, what is happening? So let's ignore this middle thing, right? We are asking what is this Mr. RS? We know who Mr. R is and Mr. S is. What about Mr. RS? So that takes 1 to 4, right? And where does 4 go? Goes back to 1. And 2 goes to 8 goes back to 2. So this is RS, right? And then 1, 2, 3 goes to 5 and 5 goes to 3 and 4 is done, 4 goes to 1, who's missing? 6. 6 goes to 7 and 7 goes to 6. Beautiful. So this is RS. And can you tell me now what is RS? RS is I, because RS is just interchanging things. If I do that twice, I get back to this. This is called a relation. So what does this RS look like over here? So 1 goes to 4, so it's going to, whatever it is going to take this to this, right? So maybe it's, can you think of something I can do to a cube to make this go to this? 1 goes to 4, 2 goes to 8, that's something very interesting. So this thing is going to the opposite thing here. 3 goes to 5, this thing goes to the opposite thing here. So these opposite things go and then these things get 6 and 7 get interchanged. So it's a very non-trivial kind of transformation of this cube. If you play with a Rubik's cube, you can actually explore these very nicely with the Rubik, because the 6 faces have different colors and you can you can tell exactly what the state of a Rubik's cube is just by looking at the positions of the different colors, so whether it's the same or not. So RS is this, and RS is I, and here's a question, what is SR? Let's just try a little bit, okay, so let's just try SR. Can you see this? Is it visible? Yeah, I think so. Maybe I can write there, so let's do SR over here. So let's look at SR. So where does 1 go? So first I have to do S. 1 goes to 1 and 1 goes to 2. So 1 goes to 2 under SR, but 1 goes to 4 under RS, right? 2 goes to 4, 4 goes to 1. So you see, it still has this property, 1 goes to 2, 2 goes back to 1. 3 goes to S, you're really good at this, 8, and 8 goes to 5, now you're like all experts, S, 5, 4 goes to, first you have to do S, I keep getting confused, 5, okay, everybody tell me, 5 goes to 6, 5 goes under S to what? 2, and 2 goes under R to what? 3, 6 goes under S to what? 6 goes to 7, no, oh God, 3 and then 3 goes to 4. 7 goes to, 7 goes to 7. Okay, so 7 goes under S to 7 and, only under S, but under R, 8, and 8 I guess, 8 goes to 6 goes to 7. Okay. So you see this SR looks a bit different. SR is 1 goes to 2, 3 goes to 5, 4 to 6, and 7 to 8. Well, the upshot is that what they taught you in school is wrong. Right? RS is not SR. In school they taught you what? A into B is B into A. Yeah, you only. I went to school so long ago, I forgot.
They didn't teach me this topic.
Not yet, okay. Somebody a little older? No? Okay, they'll tell you in school that AB is BA. And that's true for multiplication of numbers. But when you multiply these symmetries, that may not be true. And that is the source of so much interesting physics. It is at the heart of quantum mechanics. It is at the heart of Heisenberg's uncertainty principle. That transformations need not, the order in which you do things does matter. If you do this and then that, it may not be the same as doing that and this, depending on what this and that are. If you walk forwards and then walk backwards, it's probably the same as walking backwards and walking forwards in most cases. But these kinds of transformations, they don't have this. Okay, so that's one interesting point, that the symmetries of this cube, there are some strange things happening in terms of R, S, you cannot interchange the order, and you can then do things like R, S, R. RS, RS is I, you'll find that SR, SR is also I, because it's just flipping things. But you could also, R has R squared, S squared, R squared. You could do something like this. Right? And that may not be the same as RS, RS, RS. The order will matter. And so you can start doing all kinds of things. You can write down, 5 minutes left, right? Okay, I can stop whenever, so it's fine. So, you have this thing of, what order do you write them in? And then you can keep writing different expressions. And then the question is, how many different symmetries does the cube have? Right? How many different symmetries does the cube have? So group theorists, we have a way of thinking about this, which is very simple. So one thing about the cube is that there is enough symmetry that if I take this corner, I can move it to any other corner. I can take this corner and move it here by this rotation, right? I can also take this corner and move it here by doing that 2 times, right? I can take this corner and move it here by maybe rotating in this direction. So these 4 I can get. Then I can take this corner to the back, maybe here, by doing this. I can take this corner to this fellow at the back by doing this and then doing this. and so on. So I can find a symmetry which takes any corner to any other corner. All the corners of the cube were created equal, right? The symmetry takes every corner to every other corner. It has enough symmetry for that. And then if I were to fix this corner, how much symmetry does the cube have? I can do nothing, or I can rotate S. I can do S and I can do S squared. So if I fix a corner, I have 3 symmetries, and totally I have 8 corners. So that means that the number of symmetries I have, what I can do is, to get any symmetry, I can see where this corner goes, and then there are 3 possibilities. So 8 into 3, there are exactly 24 symmetries for the cube. So the cube has 24 symmetries. Is there any letter of the alphabet which has 24 symmetries? O has infinitely many symmetries. Right? Very good. So you can just rotate O by any angle, and you can even reflect it. It will have the same symmetry. So O has infinitely many symmetries. But there is no letter of the alphabet which has exactly 24 symmetries. Is there any other letter which has infinitely many symmetries? I don't think so. Okay, so we hadn't talked about O somehow in the beginning of this. Yeah. So yeah, and then you can play with this, and here's something which you can try to do if you are adventurous. Dodecahedron, right? It's one of the most, the dodecahedron and the icosahedron are 2 of the more sort of complicated Platonic solids. So this has 5, 10, what? How many vertices does it have? 20 vertices. It has 20 vertices. And each vertex has a trilateral symmetry. It has a 120-degree symmetry. So this ends up having 60 symmetries. I can do this like so quickly when I'm used to doing these things. You just try to fix something and then see how many symmetries fix that, and then if this object is symmetric enough, you just multiply by the number of things there are. So this has 60 symmetries, and you can try to write down, R and S for this. One would be rotation about a face, the other would be rotation of this. And we are able to construct these things in computers. We are able to manipulate them very, very fast. And we are able to do amazing calculations with such groups. These are some of the simpler ones. There are more complicated ones. There's this thing called the monster group. It has more symmetries than the number of atoms in the universe. And yet it is in some terms what mathematicians call simple. You cannot break its symmetry down into smaller symmetries. So there's these are, when you see a diamond, it's beautiful because of its symmetry. But for mathematicians, we have these sort of abstract groups of symmetries, and each of these is sort of a gem in of itself. And it has a lot of interplay with nature, with art, with physics, with other branches of mathematics, with chemistry, and it's everywhere. And TRG has a lovely book. But you have it, yeah. So, so it's I think it's available online. So it's called This Amazingly Symmetrical World. It's one of these old Soviet books, but these things are always the same. So yeah. Okay, I'll stop.
Now the floor is open for questions. Yes.
Thank you, sir, for a wonderful lecture. Myself, Atul Kumar, I am from IIT Madras. So my question is, when you talk about monster group, you just said it has a symmetry more than atoms in the universe. You didn't say it has infinite symmetries like O. So
Finite.
why?
Well, because it doesn't. I mean, yeah. So it's a finite group. So its construction is rather involved, and I actually don't know that much about this. But if you go to our library, you look for this book called, it's called the Atlas of Finite Groups. And then, of course, you cannot list all the elements of the monster, but you can
present it.
You can give enough information about it to do a lot of calculations, and that's called the character table. This is what I'm teaching in my course right now for the PhD students in math science.
Okay.
Yeah.
Thank you, sir.
So thank you very much, sir. Sir, initially you said that when you just do it, you are not perfectly symmetrical. Can you explain what exactly it is, sir?
Well, I mean, I have a scar here on my forehead, which is not here. That's those
it.
kinds of things.
There are differences.
Yeah.
He had a cut in the right hand, but not on the left hand.
No, mine's not yet anyway.
Okay.
But I have a watch here, for example.
Okay.
So,
Okay. Oh, one
That's
minute.
all. Nothing
Go there.
else.
Go. Yeah.
Hello, my name is Nikita from class 5 from Mangado, MVM. I have a doubt. You are just turning a cube sideways for coming at the cross. Why don't we just do it directly at the cross? Why don't we just go like this or just come like this?
Yeah, we can do that.
One more transformation.
Huh? That's one more transformation. We'll have to call it Mr. T.
Mister?
T.
We have
Instead
Mr.
of
R,
R is
Mr.
T.
S,
Okay.
maybe Miss T.
Okay.
Okay, and that's a new transformation, but you will actually be able to do everything by just doing these things one after the other. So
Many times.
So all the transformations you'll be able to get just using these two things I've
Okay.
written. But you can also do it directly. Then that's a new transformation. But that will be something like R, S, R, R. Maybe I don't know exactly. We can work it out.
Okay, thank you.
Nice question.
so,
Okay.
So first of all, amazing lecture. You're so cool.
cool.
So this, first of all, again, second of all, it is still very intuitively hard for me to digest that SR is not equal to RS.
Yes.
And does this apply all the time if we are talking about a plane, two-dimensional? Because again, intuitively, it feels like if it was a plane, RS should be equal to SR.
That's a really
numbers.
nice, very interesting question, right? So that's even in the plane, you can find some times that RS is not equal to
RS.
You take the necklace, for example. So there we had R to the power 38 is I, and we had S squared is I, but you compute RS and you compute SR.
They will be different.
So actually it turns out that RS is SR to the power 37. You can try to, maybe don't do so many, don't do 38, just take a necklace with like 4 beads, 1 bead, 2 beads, 3 beads and 4 beads, or even 3 beads will do, I think. Yeah, just take a necklace with 4 beads. So R will be 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1, and S will be 1 goes to 1, 2 goes to 4, 4 goes to 2 and 3 goes to 3. You will find that RS is not SR. So it's not necessarily something to do with 2 dimensions or 3 dimensions. This can happen in 2 dimensions.
No, even in an equilateral triangle, if you rotate by this thing and reflect.
Yeah, maybe just a necklace with 3 beads is enough.
Okay.
So,
Next.
Thank you, sir.
So,
Wait.
So good afternoon. So when you said equations have symmetry, do you mean like when we graph the equations, we get symmetry? Like
no, it's a much more subtle thing. So I'll show you, like quadratic equations, right? Have you studied quadratic equations? So if I look at the equation ax squared plus bx plus c equals 0, what are the solutions?
X. minus b plus or minus.
Okay, you weren't expecting to ask you math questions here, but I think most of us just memorize this. I memorized it in class.
B square
something
minus 4AC.
minus b plus or minus square root of b squared minus 4ac by 2a.
Ah. For AC.
Okay, so this equation has two solutions, minus a plus, this thing minus a minus. The symmetry that we are talking about changes the plus to minus. So if you write down the equation, it will be like if I call these roots, lambda 1 and lambda 2, the equation becomes x minus lambda 1, x minus lambda. And you interchange this, the equation remains the same. So there's a hidden symmetry here among numbers themselves.
Okay.
And these were the symmetries that Galois was looking at. So at that time, there was a lot of, yes, lunch break is long.
Oh, yeah.
So there was a lot of, so you can solve quadratic, everybody knows. Cubic equations also people had figured out. It's a little more complicated, but you can write down some formula like this. Quartic degree 4 equations also. Degree 5 equations people could not do at all. And so then they figured out that there's some reason why you can't do it. So there was this French mathematician called Évariste Galois. I mean, he was 19 years old when he died, and he died in a duel. He was involved in some kind of fight or something, and they had a duel and they shot him. And the night before he died, actually he had written these things down before, but the night before he died, he really wrote more and more. And he knew that, it's really quite a story. You can still read Galois' writing the night before he died, his letter to his friend. And it's just like, sends a chill down. It's in French. It just sends a chill down your spine when you read it. There's mathematics in it, and there's this imminent death in it.
Okay.
And he was he discovered these symmetries between solutions.
Okay, 3 more questions.
Yeah,
Anand,
so it's actually
Kim,
related
and
to that
one more.
question.
One minute.
I just wanted to know what was there in Galois that was not there in Abel. Maybe you can just say a few.
So Abel showed that the general equation of degree 5 cannot be solved. Galois' work tells you precisely which equations can be solved by radicals and which cannot by analyzing the Galois group. So an equation can be solved by radicals if and only if its Galois group is solvable. That was Galois' theorem. And Abel's was a kind of more specific result.
Okay. You can ask.
Hello sir, this is Veera. So actually in the actual meaning, so still RS seems to be equal to SR for me in the case of 3
Numbers.
and 5.
If you have numbers.
3 and 5. So the RS still is same.
Sorry, RS and SR.
RS equal to SR.
Yeah,
in the case
there's
of 3
something nice, 3 and 5 are the same, but 1 and 2 and then it's 1 and 4. So they're not the same. Exactly.
Intermediate step is different.
So we'll say they're the same if they do exactly the same thing to the cube. So all the things are with. But there's one thing, they're very similar looking. Right? They have these 2 cycles. They're called conjugate elements. Okay. So they have, you can't really, they're different but they're similar.
Okay.
So this, you are talking about one solid, 20 corners and 12 faces. Does it follow this Euler's formula? Vertices plus
Yeah, everybody follows Euler's.
But the edges, how can we calculate the edges? It's very difficult to.
30.
30 by formula you're telling.
Not by formula, I made it.
He made it.
To make the origami thing, you have to make 30 of those small pieces.
At least can you just show the sample? One part is showing, we can follow.
Okay, you can give that mic to her.
Well, you can count them.
Be careful.
First
Okay,
of
you
all,
can ask the question.
thank you so much for bringing math into life and into practical scenarios with your toys. You call it toys. So my question is, can the Fibonacci principle be applied to symmetry?
What is the Fibonacci?
What is Fibonacci principle?
So the Fibonacci principle is when you add, for example, from if you add
There's a
one
sequence. There's a
yeah,
sequence.
it's a Fibonacci sequence, right?
But
So if you add
what is
1 plus 2 is 3, and then you have to add the first prior numbers to get the next product.
That's a sequence.
It's a sum
But what
of,
is the
it's a
symmetry?
sequence So nature has a lot of Fibonacci sequence, right? If a shell, a sunflower and all that.
Yeah.
So I just wanted to know if Fibonacci principle can be applied to symmetry. Because in my assumption, I think in mirror symmetry, Fibonacci principle is very tough. So.
Actually, there's a very nice book by Douglas Hofstadter called Gödel, Escher, Bach. I think he talks about some symmetry. There's a spiral thing and its symmetries. Maybe you can look there.
A shell.
Yeah. But your question is very open-ended. So you're asking can. Well,
You can.
I guess there must be something. Yeah.
Okay, I think we'll move, or unless you have something more to come in.
You're the boss.
No, you are the super boss. Okay, thank you very much. We'll go for lunch.